cow, there's a pen right there. I love it. Okay, 25, 3, 1 to 15. Hello, Louisa. Hello, Alex. Hello, Penelope. Hello, Oscar. Thank you for joining me this afternoon. And yeah, we're going till 2:15 today. Hello, Alicia. And while you guys are waiting up for some others, I put this helpful reminder on how to remember oxidation and reduction. Oil rig, right? Oil rig. Oxidation, reduction, See if you can figure out what we're going to put in there. Bella, hello. Hello, Chelsea. Yeah, so as soon as you know, go ahead and make a guess, and I'll put it in here. Okay, so be it. All right, Bella. So you can watch the rest on the live stream. Hello, Errol is here too. Welcome, Errol. And I guess you guys just had a test, so you're probably all exhausted from your test. Okay, so shall we do it? Let's see if anybody's got it. So oxidation, what would be oil? Can you guess? And I'll write in the blank. And the other one, reduction, rig. So what would be the I and the G? We might have had this earlier in the year. I can't remember. Oxidation is loss. Thank you. Very good. Louisa, it is loss of electrons, or we can say, how about losing electrons? It's really the only way I keep these straight, by the way. And reduction is, thank you, Louisa, gaining electrons. It's just another of the many ways to remember which is which. Okay, do you guys have any questions to start off? In other words, any book problems you want to ask about? Now's the time to ask. Any book problems to ask about? And I'm grabbing the book as we speak. By the way, we're cutting section 7.2 because I find that the AP really doesn't cover it anymore. So therefore, we don't have to cover it. So we're cutting most of that section other than the first page. You'll be happy to know that shortens chapter 7 a bit. Our last chapter on redox. Any problems you want to ask about? Okay, well, I'll let you know this too, okay, folks? If you got problems during break, email or whatever to me and I'll help you out with them. And if I can do it over email, great. If we need to do a live meet, we'll do that because the next 2 weeks I'm not traveling to Tahiti or anywhere. So if you got some questions, I can also help you during the break. All right. I assigned 6 and 7 because I have to, because our clausure on April 21st is over all of it. So I gave you what to do and reminded you of the chapter 7 stuff to skip when you get to that one. Okay, I know it's a lot of pressure on you guys, but that's that way every year. So we'll do what we can. Today, let's go ahead then and start. Hello, Anne-Sophie. Let's go ahead and start and then work some more stuff with oxidation and reduction. You ready? All right, let's do it. We've covered most of the section 7.1 already. We had some of this earlier in the year. And I think I want to just do one with you to remind you of this. I'll show you where I'm at. I'm on page 434 if you want to look there, okay? Page 434. Okay, so we got this. It's 2 aluminum and I'm going to write the phase, that's solid, plus an Fe2O3, which is also solid. I think they're all solid. Goes to Al2O3, Al2O3, I'm trying to make a 3, which is a solid plus 2Fe. Okay, they're all solids. All right, you didn't have to do that at all. Neither did I. But now I know. Okay, they're just all solid phase stuff. Okay, so I want to talk to you about how to find out which is doing oxidation and which is doing reduction. The easiest way is to remember some simple rules, okay? O, generally 2 minus. Okay? H, generally 8, it's plus 1. And then elements, like Fe here, okay, elements, in other words, when they're alone, right, not in a compound, you know what I'm saying? Have a 0 for their charge. So right away, we can do some of this and figure it out, okay? Check this out. There's an element, so the charge there is 0. There's an element, Fe, the charge there is 0. So go ahead and mark those puppies, okay? So obviously, I must have something going on with the other ones, okay? All right, let's analyze each one separately. So you ready? Here we go. Fe2O3. So Fe2O3, I think, did we do this at the start of the year? I hope this is review. Okay, it's a solid, so it's gonna, and there's no charge up there, so it's gonna add up to 0, okay? And then I got the Fe. I don't know what charge that's gonna be. I'm gonna just say Fe times 2, so 2 Fe's. Okay, plus I got 3 oxygens in there. Oh, but oxygens are generally 2 minus, so watch this. 3 times 2 minus. You know what I'm saying? So we're making like a little problem out of this. We're making it add up to 0. That's the charge on the solid. I've got 2 Fe's. I don't know what the charge is. And I got 3 O's, and those are 2 minus. So go ahead and divide this over. So divide. So it's going to be plus 6 over here, right? Equals 2 of these guys. And therefore the Fe is 3 plus. So I'm going to write that right under the Fe. So that sucker is 3 plus. Questions on how I did that? Let's do the other one. Let's do the other one. So here we go. I'm going to do this guy. So Al2O3, that's again going to add up to 0. And I've got 2 Als, I don't know what they are, as an oxidation number. Plus I got 3 2 minuses. Is this going to be the same thing? Is that boring? It is. It's that boring. All right, sorry. So this is also 3 plus, isn't it? I thought it was more exciting. All right, so that's 3 plus here. So in other words, now let's look at what we got, okay? So I got 0. Let's put it down below. I got 0 going to 3 plus, and I got 3 plus going to 0. So which one, thank you, Anzafi, thanks for participating. Which one is undergoing reduction? Which one has a charge reducing? So the iron or the aluminum? Which one's undergoing reduction? Just to see if your brains are working. Hint, which numbers are reducing? Reducing. You really got to think of it that way. What's going down? 0 to 3 or 3 to 0? Which one's reducing? I got 2 participating. I'd like a lot more because this is really the key question you got to ask, okay? So which thing is reducing? Thank you. All right, there's another one. Good. So this is undergoing reduction. It's reducing. It's going from 3 plus to 0. Reduction. So the other one is got to be the opposite. So it's going from 0 to 3 plus. That's oxidizing. Oxidation. Okay. Question for everybody. Did we do something like this earlier in the year? Oops. Yes. Did we do something like this earlier in the year, what I circled? Yes, yes, or no, no? In other words, is it vaguely familiar or we've never done that? Figuring out the oxidation number. Bella says yes, so does Aunt Sophie. Okay, so we have done this. Thank you. All right, thanks everybody. Good. So we've done this before. Good. Then that means we're going to just jump ahead and draw ourselves a circuit. So the cool thing is there's not much to do with 7-2, so we're already up to 7-3. Yippee skippy. Skippity doobop. Okay, so let's do 7-3. And I'm going to do it my way. And I'm also roasting, so I got to take this off. Pardon me for a sec. My 1 meter studio. Okay. That's better. When last we met, we talked about a voltaic cell. Here's what I mean by a voltaic cell. It gives off energy. Okay? And that would be oh boy. All right. Cheryl calls it something else. Let me remind myself what she calls it. Hold on. Sorry, I want to give you her term too. She calls it electrochemical cell. All right. I don't really like that. But for Cheryl, electrochemical. I'll tell you later why I don't like it. Well, an example, quite frankly, is a battery. So I don't want this to be a mystery to you. You all use batteries in your phones and in appliances and smoke detectors and all sorts of stuff around the house, even rechargeable batteries, okay? If I undo my AC adapter from my laptop, then it's using the battery, it's using the akku, it's using it, meaning it's giving off energy to run the thing. So it's a battery, it's a voltaic cell, it's an electrochemical cell. We're going to look at a kind of an easy one to start out with. And it goes like this. So our example is going to be, this is called cell notation. And you're given it like this. Zn 2 plus, 2 lines. Then I got Cu2 plus, and 1 line, and Cu. So my people The cool thing about this, this is standard cell notation. This is how you show what's in your cell. We're going to draw the cell, okay, in a little bit. But for now, you need to know this side. It's alphabetical, which is cool. This side is the anode. This side's the cathode. And here's a really stupid thing, but it works. Anode and oxidation both start with a vowel. And it is oxidizing. Look, the number's getting bigger. And cathode and reduction both start with a consonant. Is that stupid? Yeah. Does it work? Yeah. So I hope that'll help you remember it. Okay. Although you can see the numbers reducing anyway. Check it out. 2 plus going to 0. That's definitely reducing anyway. Okay. But anyway, this side's always the anode and the other side's the cathode. So it goes alphabetical, anode, cathode, when you do it this way. This thing in the middle, that represents a salt bridge. Salt bridge. We're going to draw that. Don't panic. It's not a bridge you can walk across, but it's also not a big deal. But it has to be there. It has to be there. And what it does is, I'm going to say salt bridge to separate the half cells. So like each of these is half the story, the anode half and the cathode half. So the salt bridge is going to separate them, but it also connects them. Exactly. So you got an anode, and what's happening there, Anne-Sophie, is oxidation. You got a cathode, what's happening there is reduction every time. Ute, let's draw it. So it's going to be like a half a sheet of paper, just so you know what's coming, okay? And I got to erase all this because I need the whole flipping whiteboard for this sucker. But I think it'll make sense to you. Okay, so here we go. So I need essentially 2 big beakers or 2 some containers of fluid. And in one of these, I'm going to put a zinc stick. Oh boy, do I really want to do that? Yeah, I do want to do that. Okay, so I don't. Okay, so here's the zinc stick. ZN. And it's a piece of metal, okay? So it's actually sticking up. And over here is going to be a stick of copper. Cu. So that's a solid stick going like that. Then we got a solution. So I'll use blue to show that. So it's sitting in some aqueous solution. And if you look back, you can see what it's sitting in, okay? This one is sitting in, whoops, sorry, I forgot something. We got to connect these puppies too. So we're going to draw here. That's going to be the salt bridge. Okay. All right, let's finish up the drawing here. The salt bridge, it's kind of open. Thank you, Feeny. Okay, appreciate it. Good luck. The salt bridge is pretty much open, except they put in some steel, or some wool, some little kind of like fuzzy white stuff to keep the salt from like flowing out easily. So here's a little wool on both sides. It looks like something I don't know, put in your ears, okay? It's just a little white, like cottony thing. Cottony white. You'll probably see it in a picture in her book. Cottony white. Okay, that's really unimportant. I don't know why I wrote that. Anyway, let's go back and look at our cell notation, right? So we said we got Zn and we also got Zn2 plus. So that's the stuff swimming around. So you got Zn2 plus ions, okay? And I'll put a couple of those. And for the copper, we got Cu, what did I tell you? Cu plus? Or Cu2 plus? Cu2 plus. I'll put a couple of those. Now, the deal is, folks, I can't just have positives in there. I got to have some negatives in there too. You know what I'm saying? It's got to be electrically neutral. So if I got some Zn2 pluses, maybe I've got some other stuff in there too. I'll put in some like CO minuses, okay? CO minus, CO minus, CO minus, CO minus. Why? Because I got the same amount of positive as negative now. Same over here, CO minus, CO minus, CO minus, CO minus, just to make my cartoon reasonable, okay? Because you have to have electrical neutrality. We'll see why that's important. Okay, up here in the salt bridge, we got some K pluses. And we got some NO3 minuses. I'm going to just draw one right now because otherwise it's going to get so messy. We'll see why those are there, okay? We'll see why those are there. Okay. All right, we agreed from our cell notation. Go back and look at that with me. From the cell notation, God, I keep turning it upside down. Sorry. That I'm got Zn going to Zn2 plus. What that means is I've got pieces of the solid are going to the ion state. So I'm creating more Zn2 plus. So I'm going to take a little chunk off here to show that figuratively. And I'm going to make some Zn2 pluses that float off. But wait a minute, that screws up my electrical neutrality. So to have that balanced out, I got to have some of these suckers, the NO3 minuses in the salt bridge, go down. They go through the cottony white stuff and out into the solution, okay? So draw the NO3 minuses going this way to keep it electrically neutral. That way the circuit keeps running. If you don't have a salt bridge, it doesn't work. Because it's not electrically neutral, the whole thing just stops. It doesn't work at all. And on the other side, let's see what's going on. This time I got Cu2 plus going to Cu. So this guy's going to grab onto, oh hell, I'm sorry, I forgot something. I forgot something really important. Right now this cell wouldn't do anything. We need to connect it with a wire. Now it's going to do something. Sorry. Okay, so that's a wire. Because it's got to allow the what to flow. What's got to flow from one side to the other? What's really flowing here through the wire? Just so I know you know. What's flowing through the wire? Important question. Maybe you could type in an answer for me. What's flowing through the wire? Starts with E, ends with on. Okay, electrons are flowing through the wire. Don't make me nervous. You got to be able to understand that. Okay, so we got to figure out which way. All right. Thank you, Oscar. So we got to figure out which way these things are going. So think about the cell notation. Okay, so this guy is becoming Zn2 plus. It just left the Zn, so somehow it's leaving behind 2 electrons. All right, well, where are they going? Let's look over here. This side, we said we got Zn, we got we got Cu2 pluses, and they are going and they are attaching on here. So this is now going to attach on here and make more solid. So that's actually going to gain mass, okay? But the only way that works is if the electrons are going towards this side. In other words, this is your source of electrons. So I'm going to draw an arrow. My electrons are going from the zinc side and towards the copper side. Or to say it another way, not surprisingly, they're going from the anode, right? Because that's where oxidation's happening, anode oxidation. And they're going over where we got to have electrons. Why? Because we got reduction happening. And if it's reducing, right, reduction is electrons are being gained. So I've got, this is the cathode. And so anode, and what's happening here is I've got these little puppies coming off. So that's leaving here, my little Zn2 plus. So it is definitely oxidizing, I'll abbreviate that. And this side, these little puppies are reducing. Why? They're going from 2 plus to 0. Reduction, let's just say, okay. But I want you also to know the Cu here is gaining mass, okay? And that's the reduction side. Why? Because I got more of them and they're becoming neutrally charged and they gain mass there. On the other side, okay, this guy's clearly losing mass. And that's the anode. Whoa, crazy, huh? Okay, that's a big old diagram. But it's important. It's the basis of lots and lots of electrochemical, or as I call them, voltaic cells. And this thing would give off electricity. So you could theoretically take a light bulb, right, and hook it up in between here and light your light bulb as the current goes through the little wire here. It's kind of silly, but I mean, that's what you could do. You could use that electricity. In early days, that's what they did. That's how they got electricity, is huge, big, what were called wet cells. Wet cells. And they were big, giant beakers, huge things, full of chemicals. And they got electricity out of it. Pretty rudimentary, as we say now, but you know what? It did work. Okay, I'm going to erase this unless you guys got questions on this. Actually, I'm going to leave this half, and I'm going to erase this half. So you don't have to draw it twice, but you can maybe draw the right side again down here. And I'm going to draw a new cell notation. And, well, let me just get drawn, okay? Here we go. Mr. White, shut up and draw it. Here we go. And this time, I got to show you what we got. We still got the salt bridge. There's a little cottony stuff at the end. And well, let's tell you what's going on. Okay, here's the cell notation for this one, right? It's going to be the same thing on this side. Zn go into Zn2 plus. And then separation. So there's your anode. Here comes the cathode. The cathode's going to be just H plus going to H2 gas. So this one has something on the right side, the cathode, that's not a metal. How do we work that? It's not so hard. I'll show you. What happens is you have the wire come over and you have it go down in here and you attach it at the bottom to a little piece of platinum, PT. Platinum's known as an inert electrode. It's not being either used up or anything. It's just a place to get electrons or give off electrons. Inert electrode. And you might say, well, how does that work? Well, it's all right. It works pretty well. What you do is you put it in a test tube. So it comes through the test tube. And then you put a little spigot here because you don't want the thing to explode. And out the top, you've got a source of, what are we making? H2 gas. So that's going to come out here. And you can store it in a container however you want to do. And then the rest of it looks the same. Why did I do this? I did this because I want to show you that sometimes I've got an electrochemical cell or battery that doesn't involve a chunk of metal. So this one involves only HCl down here, H plus, Cl minus, Cl minus. And you can guess what's going on. The H pluses go here, and they grab onto electrons, and they make H2 gas. I'll take your questions in a sec, don't worry. And so what's got to happen is, if the H pluses are leaving, somebody like K plus has got to come out of here and go down into the solution to replace the positives. Remember, I got to keep this thing electrically neutral. So if the H pluses leave, I got to have something positive replace that to keep the thing electrically neutral. Okay, let me see if you got some questions here. I don't like electrochemical cell, Anne-Sophie, because the opposite of that is called an electrolytic cell. And to me, they sound too much the same. But if I think of voltaic cell and the opposite electrolytic, they sound quite a bit different. I don't like them because they sound the same, but that's what Cheryl uses. The Zn loses mass. Yep, exactly, Penelope. So in this new one, I've still got the Zn going to Zn2 plus, so it's losing mass. The Zn2 pluses are ions floating around. So this stick gets smaller and smaller. This stick, the platinum, is not changing size. It's not gaining mass. All that's happening is it's a source for these things to glom on, and then they create H2, and it goes to the top, and then it just goes out the little glass container, pardon me, to wherever you're going to store your hydrogen gas. All right? Ute. Okay. Good questions. Any other questions before I erase all this thing? So they're kind of intricate, but if you think about the little parts, they do make sense. And they're all pretty much the same. I got the anode, I got the cathode. One side's gaining electrons, one side's losing. And you can usually figure out from the chemicals what's happening. We're going to do that right now. Okay? All right. Here we go. Let's try one together. Let's try one together. Here we go. So here's an example. I got Cl2 gas plus 2 Br minus, and that's an aqueous solution. I'll make double arrows. Forms 2Cl minus, and that's, of course, in solution, aqueous, plus Br2 liquid. This is another weird one where it won't be a chunk of metal, right? In fact, it's got a gas and a liquid. So this would be a hard cell to make, but it doesn't matter. What I want to ask you is, what's the cathode reaction? So what's the cathode reaction? Or we can also call it, ready, the reduction half reaction. It's called a half reaction because it's like half the story, all right? And then, of course, I'm going to ask you, you know what I'm going to ask you. I'm going to ask you then for B, what's the anode reaction? Otherwise known as the oxidation half reaction. Half reaction. Good, let's do it. Okay, so who's reducing? Who's reducing? Cl or Br? Look at the charges. Who's reducing? Cl or Br as I go to the products. So when I get over here, whose charge has reduced? Thank you, Anne-Sophie. Let's see if some others have chimed in as well. Yeah, because this is 0, right? And this is 0. So the only one that's reduced is the Cl. All right, so let's go ahead and write that half reaction. A lot of you had that too. Chelsea and Errol, Penelope, Alicia had that as well. So here we go. Cl2 goes to 2Cl minus. But you know what? I got to add some electrons to have this happen. So check it out. I've got 2 Cl minuses. So don't they need 2 electrons? So plus 2 electrons. And that, my friends, that's the half reaction. And that's the reduction half reaction right there. Okay? Well, let's do the other one. Okay, so the other one's going to be the oxidation half reaction. So it's got to be the other guy. So I got 2 Br minus. And you can tell if you had to, you could balance this, right? Because you need 2 of these, obviously. Okay, going to Br2. I'm going to leave the phase off for a second. And that's 0, so that means I've gotten rid of a couple of electrons. 2 electrons because 1 for each of these Br minuses. And that is the other half reaction. Notice, if I add these 2 together, what do I get? I get this. So this sucker up here, this is called the redox reaction. Redox, because it's got both together. Makes sense, right? So I got a half, and together they make the whole. And notice, when I add them together, what drops out? When I add them together, what drops out? And that has to happen every time, by the way. What's dropping out? While you're thinking, I better get thinking too. I think we're doing darn good. You got it. Thank you, everybody. Good. Yeah. Chelsea and Sophie. Electrons. The electrons got to drop out. And if you think they will every time, right? I'm not going to cross them out here, but so there's 2. There's 2. It doesn't always have to be 2. Could be 1, could be 6, whatever. But they're going to cross out to make then a redox reaction, which just has it happening within the reaction. Okay, why is the second one a half reaction? Well, each one tells a little story, Bella. This is telling you that the Cl minuses are grabbing onto electrons and getting reduced. Sorry, backwards. The Cl2s are grabbing onto electrons and getting reduced to Cl minuses. The other story is these are the Br minuses, and they're giving up their electrons to become Br2. So it's just 2 stories. One is gaining electrons and one is losing electrons. The gaining is reduction, losing is oxidation. So Each one we say is half the story, Bella. So if I put the two halves together, then I get the whole thing that's happening in the beaker or wherever it's happening. Let me know if that helped. It's half the story. Half the story. Good. We're going to skip all that and go right to here. Okay. Any other questions from you about half reactions? Let's do another one. Okay. Let's do another one. And this time, we're going to do something new with it as well, but not something hard. Okay. We're going to get E0. E0 is called the standard voltage. Of the cell. Okay? Standard voltage. Where do you get that? Okay, I'm going to tell you. In your book, I'm going to tell you right where the data is. You ready? Here we go. Grab your book and turn, as I'm turning, to page 523. You really have to have this to do this. And you'll see that it's pretty cool data, although they wrote it so frickin' small, you're going to have to help me. That or I got to go get my glasses. Holy cannoli. Okay, let's get the standard voltage for this cell. You ready? So example, get E0, the standard voltage for, and here it is. It's one we talked about at the beginning, Zn2 plus, Cu2 plus, going to Cu. Okay, so I'd like you to look back in here and find these half reactions. Now, I got to tell you, look at the top of the column on page 523. It says these are reduction half reactions. All right, that's fine, but it means you're going to have to do what with one of them? If these are reductions, half reactions, what are you going to have to do with one of these things? And also get looking and find the one with zinc and find the one for copper. And make sure it's Cu2 plus and Cu, okay? Are you with me out there? I need to know. So what do you got to do with one of them? They're all reduction half reactions. I got to take one of these reactions and... All right, well, let's just think while you're thinking. Okay, so here we go. Which side is reducing? Well, of course, anode cathode, this side's reducing. Look at it, 2 plus going to 0, so that's reduction. But this side's oxidation, isn't it? So you know what? I got to find that reaction with zinc, and I've got to then flip it around. Oxidation, flip. All right, let's do it. So everybody find the zinc one. Okay? I wish you guys were here. I could ask you. I want to make sure you can use this data table. It's really important you can use this and you know where it is. And also I could use your eyes. I got zinc 2 plus plus 2 electrons goes to zinc, and it's negative 0.76. And that's volts, by the way. Volts is what we measure our potential in. All right, let's find the other one. the Cu, 2 plus, and Cu. And there's a lot of Cu ones, so you gotta like make sure you get the right one. I think I got the right one. If I could see it, it's 0.34, is that right? So Cu2 plus 2 electrons forms Cu, and it's 0.34. Now, check this out. Cu2 plus Cu, Cu2 plus Cu. Look at the other one. Zn, Zn2 plus, Zn2 plus Zn. What's the problem here, gang? Look at that top reaction. What do I got to do? What's the problem? What do I got to do? What's the problem here? It's essential that you can see that. Thank you. Okay, Chelsea, we got to flip it around. So we're going to do that. You ready? I'll put a line through it. Write it backwards. You might say, well, Mr. Weiss, how do I know which one? It's the one that's the oxidation. So the reduction one is as is, but you got to flip the oxidation one. So we're going to do it. So that's going to be Zn going to Zn2 plus, right? Because that's what my little thing says, Zn2 plus 2 electrons. Now, add her up together. Add her up. Ready? Check this out. The electrons cancel as they should. So 2 electrons on each side. Again, it's just by, I forgot here. Sorry. What happens to the voltage over here? It was negative 0.76, but I flipped it around. And Anne-Sophie's got it. It's now going to be 0.76 volts. Ta-da! Okay? All right, add this sucker up. So my redox reaction is Cu2 plus a Zn, the electrons crossed out, forms Cu plus Zn2 plus. And if I get this, it's like 1.10 volts, right? That's a pretty good voltage, by the way. And that's the deal. If it's a positive voltage, you'd probably figure this out right now, okay? So if it's positive voltage, means it's going to give off energy. So it's exothermic. But if it's a negative voltage, you got to put in energy, so it's endothermic. If it's a negative voltage. Makes sense, right? Good. Again, questions from you. Now I see some participation. Good. Keep that coming. Think as much as you can. I know it's a tiring day. I'm a little wiped out myself here. Okay, so that is really, really good. Another way to say this, I'll leave that over here for now. Some comments on. Yes, okay, Penelope. Yes, if it's exothermic, what's negative is the change in heat, and it's going to give off some energy. This time, instead of heat, it'll be giving off electrical energy. So it won't be delta H that we're talking about. But if it were delta H, if it were giving off heat, that would also be exothermic. Yeah, so that's the correct sign for delta H. But for voltage, it's got to be positive. So some comments about voltage, okay? Where do I want to put that? Okay, so comments on voltage. Comments on E0, otherwise known as voltage of the cell. I got to get a new blue. You can't see squat. I'm throwing that one away. Let's go to red. Okay, comments on E0, the voltage of a cell. One is that the E0 better be positive for the cell to run spontaneously. Remember that word? It's not delta H, but delta somebody else, isn't it? So E0 better be positive for the cell to run spontaneously and give off energy. En for energy. Second, if you multiply, we're going to do this in a second here, multiply a half reaction by a number, you don't multiply the voltage by that number. Okay. Why? Let's find out. And we're going to do one so you understand what I'm talking about. Okay, so if I got a half reaction, like this is a big difference. Penelope, you mentioned delta H. For delta H, the more stuff I've got, the bigger the delta H. It's going to be more heat given off if I have more material. For this, it doesn't matter if I got more material because voltage is not the amount of energy. Voltage is like it's like the drop off a cliff. So here's the cliff, right? Cliff. The height is like voltage. However, the amount of water coming over, here comes the water. Whoa. Think of like a waterfall. Okay, a waterfall. So the height of the waterfall, that's like the voltage. That doesn't change. The amount of water coming over, so the water could be like the number of electrons. I can have a lot of electrons flowing, and maybe that means I'm making a lot of a solid, or I'm making a circuit run, a lot of electrons are flowing through, or I can have very few. But that doesn't change the height of the cliff. I can have a little water going over or a lot. If I have a little, that's like a small number of electrons. If I have a lot, I got a lot of electrons. But the height of the cliff, that's the voltage, okay? So voltage doesn't change. So even if I multiply something by a number, it doesn't change the height of the cliff. The voltage stays the same. Let's do one right now. You'll see what I'm talking about, okay? I know I'm blathering on and on today, okay? I know that. Okay, I'm going to take something from the back of our book, our data, and do it. First, let's do one more cell notation. Okay, so anode, anode oxidation. So we're going to go Al. Oh boy, I got to find this sucker. Al to Al3 plus. Man, they could have written this smaller, but I don't know how. Give me a number, somebody. Where's Al? Back of the book. There it is. There it is. Okay, so I got Al. Al going to, so that's oxidation, anode. So I got Al going to Al3 plus. And then I got like I2 going to I minus. Okay, here we go. The half reactions. Okay, the one undergoing reduction is this one, right? You can tell it's getting more negative. So the I minus one's going to be like this. I2 going to, no, plus 2 electrons goes to 2 I minus. Everybody okay with how I balance that? Makes sense? 2 I's, 2 I's. Got to add 2 electrons to make them both negative. Okay, now the voltage of that sucker is 0.54. Am I reading that right? I hope so. 0.54 volts. Good. You'll see where I'm going with this. The other one, the aluminum one. Golly, I just found it. Where the frick was aluminum? Negative 1.6. So I got to flip the aluminum one around. So that it's going to be Al. How do I know that? Because it's up here. Al goes to Al3 plus 3 electrons. Okay? The voltage, I flip this one around. So I got to change the voltage, don't I? So it's 1, not negative, it's positive now, 1.66 volts. Okay, now, see how I got, I'll put pluses here so you know that's part of that. Check this out, 3 electrons, 2 electrons, not good. I need to have the same number of electrons, so I need a common multiple like you and I have done so far. Thank you, Anne-Sophie. Glad that's the checks with the same number I got there. Okay, so here we go. 2 and 3. I'm going to multiply this by 3. And I'm going to multiply this one by 2. Because I got to have 6 electrons on each side, don't I? They got to drop out. So my redox is going to be what? It's going to be 3I2 plus 2Al, 2 chunks of aluminum, makes 2Al3 plus 6I minus. Now, all that multiplying does not affect these suckers at all, okay? So that's what I mean by don't multiply anything. Remember, the height of the cliff is still the same. So add these together for me. It's going to be what? 2.20, is that right? 1. Does that look right to you? Let me know if you get the same thing I do. Exactly. Exactly. Does that look right? Did I add that correctly? That's my cell voltage, isn't it? Ute. Ute. Questions from you? I want you to notice something here. Hey, a positive voltage means it's going to be spontaneous. I know we said that earlier, but what does that mean? It means I'm going to have what? A negative delta G. Remember, it gives free energy. If it's negative, it's spontaneous. And what about the equilibrium constant? Will it be more or less than 1? Will it be more or less than 1? Thank you, Penelope. Notice we're combining ideas from different parts of the year now. So if it's spontaneous with a positive voltage, it's going to be a negative delta G. That was also spontaneous. What about K, the equilibrium constant? How will it be compared with 1 if it's spontaneous? K will be what sort of number? KEQ, or just K. What sort of number will it be if it's spontaneous? And I really need an answer from everybody, so really think about it. If it's a spontaneous reaction, what sort of numbers are going to be for the equilibrium constant? We just had a quiz on that. It's a negative delta G, so it's spontaneous. Positive voltage. Hint, it's going forward a lot. What sort of number will K be? Alicia, thank you. Greater than 1. Remember K, right? If it's 1, it's not really going anywhere. If it's going towards the product, so it's spontaneous, it's going to be greater than 1. This would be probably much greater than 1. This would probably be a really big K, because that's a pretty high voltage. 2.2 is a big voltage. So it's very favorable. It'll be very much a negative delta G as well. You think there are equations to get those, one from the other? You betcha. You're going to see all those for Cheryl. If I know the voltage, I can get the delta G. If I know the voltage, I can get the K. If I know K, I can get delta G. Any of these three, bum, bum, bum. You'll be given all those equations on the AP, by the way. Isn't that nice? Makes sense with our whole year, doesn't it? So spontaneous means all of that. Ute. Ute. I'm going to save that. Let's just check something, okay, and see if it's spontaneous. So here's a little question. Will Cu be oxidized to Cu2 plus by HCl? In other words, if I put copper in acid, is it going to react? Believe it or not, we're going to find that out by checking out the voltages at the back of your book. So look and find one with, well, Cl minus is nothing, right? It's a spectator, but it's going to be the H plus. I want you to look for that. And I want you to look for one going from Cu to Cu2 plus. And can you find the voltage for that while I write it down? So it's going to be Cu goes to Cu2 plus 2 electrons. Okay, everybody, what's the voltage? Pop, 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 volts. Can you find that for me? You're looking at that table at the back of your book again, page 500, whatever. It's important that you can find those values. So what's the voltage for Cu going to Cu2 plus, and you got to have it that way. So please look at page, what is it, 535 or whatever I told you. No, 524. No, 523. 523. Alicia, negative 0.15. Is it that? I got a different one, Alicia. Could you look again and see? I got Cu going to Cu2 plus. Be careful, there's a lot of coppers on there. And then Sophie's got 0.34. Yeah, that's the one I got. 0.34. Is it positive or negative, Anne Sophie? Is it positive or negative? Check out the way we did it. It's oxidizing, so you got to change the sign on it. You know what I'm saying? And I don't know what sign was on there, so you got to let me know. Did you change the sign? Thank you. Okay, so it's negative. Good. So you got to flip the sign. And the other one is H plus. So check this out. H plus. And that's like this. If I got two of them and they add 2 electrons, I get H2 gas. And oddly enough, the voltage for that, because it's what the whole system is based on, is 0. So my total is negative 3.34 volts. And I can cross out some things here. And here's my redox, which would be 2H plus Cu forms Cu2 plus H2. But I didn't answer the question yet, did I? So look back at the question. Will copper be oxidized by Cu2 plus? Will copper be oxidized to Cu2 plus by HCl? Check out that voltage. So what's the answer? Yes or no? Will it be oxidized to become Cu2 plus? So by looking up the numbers, what did you prove? This is kind of a powerful thing. You can prove whether a reaction is going to happen or not. And if it's negative, is it going to happen? Negative voltage. Not negative delta G, it's a negative voltage. So voltage and delta G got opposite signs, don't they? So the answer is, and there's somebody. It's what number it is. It's they base the system on that, Anne Sophie. But if you look up in the back, that's what it is for H plus going to H2. Well, the answer is no. Right? Why? Because I got a negative voltage. So it's not spontaneous. It's not going to happen. Questions from you about that? The only way this would happen is if I put in energy, but that's a different sort of cell. In other words, it won't give off energy on its own. It's a negative voltage. Not going to happen. Okay. Same question, almost. We're going to change the acid. Will it be done by HNO3, nitric acid, instead of HCl? Well, this one's still the same. It's negative 0.344, or negative 0.34, right? But check out this reaction now. We got NO3 minus I know you always thought it was a spectator. It turns out it does things electrically. If you got it with H pluses. Plus 4H plus goes to NO. I hope I got this right. My eyes were better last year. Plus 2 waters. Plus some electrons. Plus 3 electrons. Okay, so obviously I got to multiply this one by. Oh, and the voltage for this is, ready? Voltage is 0.964. And of course, I'd have to multiply this one by what? 3, and this one by 2. But I think you see it, right? So I get 0.625 volts. So is this going to work? And the answer is yes. So interestingly enough, if I have copper in HCl, it doesn't do anything. If I put copper in nitric acid, HNO3, which I do because I create some gas for you, NO gas, when I do a demo for you, that really reacts. And it's a very positive voltage, so it's spontaneous, okay? All right, I didn't take the time to add these, but you could and write the redox reaction down there. But really, we've answered the question just by checking out the voltages, haven't we? Does it work? Is it spontaneous? Yes, yes, no, no. Yes, yes, positive voltage. No, no, negative voltage. Huge. Let's do a review of the last little thing here, okay? Because it's so important. Review. E0, K, big K, and delta G. And over here we got spontaneous. And here we got non-spontaneous. So this is kind of a review chart for you, okay? So let's do E0 first, right? We said it's spontaneous if I got a positive voltage, right? And it's not spontaneous if I got a negative voltage. So there's my minus sign there. For K, right, it's spontaneously if it's, we got this from Alicia earlier today, if it's greater than 1. It's not spontaneous if it's less than 1. For delta G, it's spontaneous if that substance is negative, so it's the opposite sign as the voltage. Remember, E0 is the voltage, all right? Don't get all weirded out. E0 is the voltage. Okay, and if it's a positive delta G, that sucker's non-spontaneous. So that brings a lot of the course together, doesn't it? Good. Done for the day. I will see you after break, and we'll finish up with chapter 7, although frankly, you have enough to do it now, I think, in your head. So if you get that far. Work hard. Let me know if you got questions during break. Write me emails or whatever, okay? And I'll help you out. All right, be well, my people. We're getting near the end. Hang tough.